Okay, so we go back to the theory of differential geometry in this lecture. We start by talking about the divergence of a vector field. Now, there are a number of concepts that we can define on a manifold only if we have a metric. So we saw that, for example, the differential of a function is a concept which we define immediately after the definition of a manifold. The gradient of a function, we need the metric, but again, we have the differential. The Hessian of a function cannot be defined without the metric, or at least without a connection. But then again, let us consider a Riemannian manifold. Given a vector field, its divergence is the function div x from n to r given by minus the trace of the covariant derivative of x. Now, first thing first, this minus is inconsequential. I mean, half of the references will tell you minus, the other half will tell you plus. Why? Well, because it depends on what you're using it for. Essentially, to make some integration by parts formula true, you need, I mean, nice, not true, they're always true, but to make them nice, you need the minus. To make some other formulas nice, you need the plus. So it depends on what you're using it for. I only hope I've chosen a consistent determination of the signs. So I hope the lectures are orientable. Anyway, what does it mean to take the trace of the covariant derivative? The covariant derivative is an endomorphism of the tangent space. At each point, nabla x is a linear function from the tangent to the tangent. So for each vector, it gives you a vector, because for each direction, it gives you the variation of your vector field in that direction, which is another vector. The first order variation, which is another vector. So its trace at P is a well-defined value, because if we have an endomorphism of a linear space, its trace is well-defined. In local coordinates, if we write this as Dij, dxj tensor partial I, so this is the common basis for the endomorphisms, one upper index and one lower index. The trace at P is dii. So the sum of the terms on the diagonal, the trace. More explicitly, this is the expression for, we substituted the expression for the covariant derivative, so it's the ith derivative of the ith component with a minus, minus gamma I ji xj. Now, let me recall that in general, these two indexes cannot be exchanged. So gamma I jk is not symmetric in j and k, but it is as soon as the connection is without torsion. And we will always be using a connection without torsion and compatible with the metric, which is unique, and it's called the Levi-Civita connection. So that everything goes well with the parallel transport and stuff like that. So again, if you choose the other sign, you will get plus signs here. Now, we can define also everything for a differential form, as I was saying in the starting of the previous lecture. So, I won't be going into much detail again, but a differential form is a section of T star M. So at every point you get a linear functional on the tangent space at that point. Using the metric, if you get a section of T star M, which let me remind you, are denoted by omega 1m, the sections of T star M, differential one forms on M, we define the covariant derivative of alpha at P as this bilinear form. So the bilinear form that sends x and y well, this would be the writing, and this is the definition. The scalar product between the covariant derivative of alpha sharp against y. The covariant derivative along x of alpha sharp against y. Or, more compactly, this part, which is the same thing that I did on the Hessian at the beginning of the previous lecture. So anyway, everything we do on fields, we can do on differential form. We won't be using this now, but just so you know that the covariant derivative, once you have the covariant derivative on vector fields, you can define the covariant derivative of everything, at least everything that transforms good from one chart to the other. So you cannot do the covariant derivative of Christoffel symbols, and we are all glad for that, because Christoffel symbols are terrible. Anyway, the codifferential of alpha is the function delta alpha, which is minus the trace of the covariant derivative of alpha sharp. So alpha sharp is a vector field, and we take minus the trace, which is minus the trace of the bilinear form given here. Anyway, I won't be losing too much time on that. Divergence for the Levi-Civita connection. So if our connection is the Levi-Civita connection, the term gamma I j I x j that is involved in divergence becomes the following. So this is gamma I j I. So this is gamma with I and I. Okay? So notice that on their own, these two terms are not the same. But when you raise one index, when you contract these two indexes, so you are doing a summation both on S and I. So, I mean, this one is not equal to this one, but the sum of these and the sum of these cancel out. Because we just exchanged S and I, but then we are summating over all S and I, and this term is symmetric in S and I. Whereas these two terms are anti-symmetric, because if you exchange S and I, you get a minus term. From here to here, you get a minus term. So when you do a summation over all S and I, these two terms give 0. So you end up only with this term, and so you end up with this expression. Now some magic with the metric. Let's consider the determinant of the metric. The determinant of the matrix given by the metric. Now, if you derive this with respect to jth variable, you can write it as the derivative of the determinant with respect to the matrix element times the matrix element derived with respect to the variable. Again, summation over I and S understood. And this part is the minor attached to GIS in the expansion of the determinant. Therefore, by the cofactor formula for the inverse, you get that the GIS above, which is the inverse of, is the IS element of the inverse of the matrix G, is 1 over the determinant times the cofactor. So if you put everything together inside the formula we wrote before, we end up with this. And we recognize that, I mean, we put everything together, so we simplify the part with the Christoffel symbol, and we recognize the derivative of a product. We end up with this formula. The divergence of x is minus 1 over the square root of g partial derivative in J of xj times the square root of G. Square root of G is well defined because G is positive definite, the matrix, so the determinant is positive. Obviously, if you choose the other sign, you will get a plus here, again. So you see the divergence in, in Rn, the matrix of the metric is the identity, so this determinant is 1. So you get, well, minus or plus, depending on the definition, the sum of the ith derivative of the ith term, so the usual divergence, the one you would write nabla dot times the vector. I think you all saw that. Now, once you have this, the Laplace-Beltrami operator, Riemannian manifold, smooth function, the Laplacian of f is the function Laplacian of f given as minus the divergence of the gradient or minus the codifferential of the differential. Now, why is it called Laplace-Beltrami? Because you have a number of Laplacians on a manifold. You have the Hodge Laplacian, the Lichner-Horowitz Laplacian, the Laplace-Beltrami operator. I mean, you can define them in a number of ways. The one we're interested in today is the Laplace-Beltrami operator. By the way, if you use this formula in Rn, you will just get the trace of the Hessian matrix, what you would call the Laplacian in Rn. So everything makes sense if we are in Rn. Now, if you want to express the Laplacian in local coordinates, in general, it gets, well, messy. For the Levi-Civita connection, we use the formula from before of the divergence, and we get this. So we need, here we just need to raise the index of, so in place of our, in place of our here, in place of our vector field x, we put the gradient of f, and here we get minus minus, so it's a plus. Nope. So this part here is the gradient of f, so is taking the differential of f, which has coordinates partial if, and raise the index with the inverse metric. Again, if the metric is the identity, the inverse metric is the identity, so everything is 1, and you get everything is 1. The square root of the determinant is 1. Gij is delta ij, so it's 1 if they are equal and 0 if they are different. So the only terms that survive are those where j is equal to I, so you get partial if, which is the usual Laplacian. By the way, just a notational thing. In the most pure form of Riemannian geometry notation, this does not make sense. Because we should only sum over in one lower index and one higher index. So strictly speaking, this does not make sense. However, it is understood as in normal coordinates. So in principle, taking twice the derivative of f with respect to a coordinate in local coordinates is not the same as this expression. However, if we are in a local system of coordinates which are normal and we are in the origin, then these two expressions coincide. Anyway, there is no clear way to make sense of these in Riemann geometry. So sometimes, if everything is done in normal coordinate in a point, then we can allow for such expressions, but in general the correct ones are of this form. So something up and something down, which are equal, and so you get the sum over them. Okay, it's not right, I don't know why. Who cares? I wanted to add only at the origin, but I told it. I said that already. Okay, now integration on a Riemannian manifold. We want to study some properties of the Laplace-Beltrami operator, but in order to do this, we need to spend a couple of words about integrating functions on manifolds. In Rn, the volume of the name is parallelotope, generated by n vectors, is given by the square root of the determinant of the Gram matrix of the vectors. So we take the pairwise scalar products, we arrange them in the obvious matrix, and we take the determinant. The square root of the determinant is the volume of the parallelotope. This suggests to use in a chart the measure of volume given by the square root of the determinant of the metric times dx1 dxn. So dx1 dxn is the Lebesgue measure, the standard volume in a chart with coordinates x1, xn. This gives you at each point the infinitesimal volume ratio between the volume of the parallelotope given by the metric and the volume the volume of the parallelotope given by the standard frame and the volume of a unit cube for the metric. So at each point of the tangent of the manifold, you have the tangent space, you have a local frame. So you have your manifold, you have your tangent space, and here you have the local frame partial 1, partial n. Okay, so you specialize these derivations at the point, and they give you tangent vectors. So they give you a basis of the tangent space. Now, in general, this is not an orthonormal basis for the metric, okay? So what can we do? We can compute now the metric G sub P is a honest scalar product on the tangent space. So it's a bilinear form. It's not something smooth that varies. It's just a symmetric matrix. So we can compute the ratio between the volume of these of the cube parallelotope spanned by these vectors against the volume of a unit cube, which by definition is 1. So we would like to write the square root of the determinant of GP applied to partial I partial J, which is the same thing as before, the Gram matrix of the basis vectors. But this is just the square root of the determinant of the matrix given by the elements Gij. So this is the infinitesimal comparison between the volume of the basis we have, the local frame, the basis we are working in, and a unit parallelotope for the metric. Obviously, we could perform a Gram-Schmidt orthonormalization smoothly on an open set and end up with a local frame which gives you an orthonormal basis at each point. But then you should compute the change of coordinates, and who knows, I mean, then difficulty is shifted towards the change of coordinates. So this is just the version on TPM. Now, if we want to compute on TPM another volume of some other vectors, we don't need to do, I mean, we get some new vectors, okay, V1, Vn, we want to compute that volume, the parallelotope generated by them. We don't need to do again the whole matrix computation. We just need the following. Okay, well, if you know what it is, we need to apply this correction. So the determinant we just found. Times the alternating form. Why? Well, because if you consider the matrix given by the coefficients of your n new vectors, so these are the coefficients of V1, Vn, with respect to the standard basis we had, the local frame basis. Now, the determinant of these scalar products yeah, okay, I tried not to care, but here we should write them with the right So this is the determinant of AIK IKG KH AHJ. Now, if you do all the computations, this is just the determinant of A squared times the determinant of G. And this is the standard representation of the determinant as a multilinear alternating form. So this part takes the determinant of the vectors, and this is the correction. Now, you need a square root of all these, so you need the determinant of A square root times the determinant of G. Okay? So this is why we write down, I mean, this is the infinitesimal volume at each point. So if we have not a basis of the tangent space, but sections of the tangent space giving a basis at each point, we can compute the volume of their parallelotope at each point, and this will be the determinant, the square root of this determinant, which is now a function of the point, times this multilinear alternating n form, which is the determinant. Now, anyway, this can be interpreted just, I didn't write the wedge product here because this is now just the Lebesgue measure in n coordinates, and this is just a function, a positive function by which we multiply the Lebesgue measure. Luckily, when you change charts, as long as the determinant of the Jacobian matrix of the change of charts is, change of coordinates is positive, so that we don't disrupt the square root, this definition is invariant under change of coordinates. So we change coordinates, from the determinant we get out the determinant of the Jacobian matrix. From the Lebesgue measure part we get out another determinant of the Jacobian matrix, and luckily they are determinants of one matrix and its inverse, so they cancel out. The only thing is that here it will get out at the square root of the determinant of A squared. So it's the modulus of the determinant of A. So we should be able to select always change of charts which have positive determinants so that they cancel out. Otherwise you will have a plus minus sign all around. If we can cover our manifold with charts such that when they overlap, the change of coordinates has a positive determinant, Jacobian determinant, then we have a global volume measure on our manifold, which locally coincides with the sensible one. Manifolds with such a property, so if we can choose change of coordinates which have positive determinant all over the manifold, so for the whole atlas, they are called orientable. So if you want to be formal and technical, an orientable structure or an orientation is a maximal atlas with the added condition that all the change of coordinates should have positive Jacobian determinant. But anyway. Now, why is it called orientable? Well, because positive determinant means that we are preserving the orientation of the basis. So think about it in R3. positive determinant means that we can move smoothly from one base to the other without having to flip anything. So we don't have reflections with respect to the plane, for example. So we can give an orientation to each tangent space in a sensible way, in a coherent way all along the manifold. Now, if we have an open domain with a smooth boundary, the boundary is a smooth hypersurface inside M. So we can give M, this boundary the structure of a smooth embedded n-1 manifold. If the ambient space is Riemannian, we have a Riemannian metric on this submanifold just by restriction. And if M is orientable, then we can orient the boundary in a compatible way. This gives us a volume on the boundary. Obviously, if the volume on M is n-dimensional, the volume on the boundary is n-1 dimensional. In practice, for example in R3, what we are doing is the following. We have our boundary will be like surface of the sphere or something like that. So this is the boundary of U, where U is the set of vectors with norm less than 1, for example. In R3, we have the measure of volume, which is just the Lebesgue measure. Now, what happens? When we orient the boundary of the sphere, it means that at each point on each tangent space, we can define a positively oriented basis of the tangent space. So we have let's say D1, D2, which is okay, and we have, I don't know, let's screw this up. So if this is the first one, this is the second one, this is, for example, this is not okay, and this is okay. So this is oriented, the blue one is oriented with the right orientation, the red one is not. So now, if you, in R3, if you compute this vector product, will give you a well-defined normal to Bu distinguishing U from R3 minus U. Okay, so this will always point, depending on the orientation you chose, inward or outward with respect to the boundary. So the volume on the boundary, let me write this. It's not I mean, it's not proper, but let me read it. Applied to two vector fields x1, to two tangent vectors x1 and x2. So I want the volume, in this case the area of the parallelogram. Well, this will just be the volume on R3 of x1, x2, and nu, where nu is this well-defined normal. So at each point, we will have our outward pointing normal, for example. And so the area of this on the tangent space at the sphere is just the volume in R3 with the last vector taken as the unit normal. So if you generalize this construction, I don't want to be too much precise, but I hope this picture helps understanding what is happening. Again, if the boundary is orientable, we have a section never vanishing of the normal bundle, and we can consider the unit norm section, nu, inward or outward, it depends on your choice of signs. With these assumptions, we have that if U is a compact open set in M with a smooth boundary, the integral on U of the divergence of X in the volume is minus the integral of BU of the scalar product between X and the normal. So this is the divergence theorem. Here is the volume integral of the divergence, and here is the flux of X through the boundary. So this holds exactly as in the flat case. We only have, you saw, we had to define what the divergence is, what the normal is, what the integral is. So we had to give meaning to everything, but once you do it carefully, everything makes sense and falls in place exactly as in the Euclidean case. Now, some property of the Laplacian. The scalar product between the gradient of f and the normal to the boundary of an open set is the normal derivative of f. First of all, the Laplacian of f is the trace of the Hessian of f. This holds true also in the Riemannian case, only the Hessian is weirder. Okay, it's not the Hessian of f with respect to local coordinates, but it has another term. Secondly, the green formula. If you consider this, oh, this is f1, not d1. So if you consider two functions, f1 and f2, the integral over u of f1 Laplacian f2 minus f2 Laplacian f1 in the volume is minus the integral over the boundary of f1 normal derivative of f2 minus f2 normal derivative of f1 in the volume of on the boundary, then minus one dimensional volume. This is just the green formula on a manifold. Now, for other random properties, if M is compact, connected, and we have a function which has which is superharmonic, so which has non-negative Laplacian, then F is constant. M has to be compact and connected. Whenever we say compact for a manifold, okay, we never talked about a manifold with boundary, but as we are talking about boundaries now, compact means without boundaries. The sphere is compact. The unit disk with the circle of the boundary is not a compact manifold. It's compact with boundary. Again, if M is compact and connected, then the integral of f times the Laplacian of f is the integral on M of the scalar product between the gradient and the gradient, so is greater or equal than 0. spectral theory. Now, we will be talking about two objects, compact Riemannian manifolds mainly, or complete Riemannian manifolds, but then we will consider only things, objects that have compact support. So functions which vanish outside the ball, or vector fields which vanish outside the ball, and so on. So everything we will talk about will be either on a compact manifold, so where everything is compact by definition, or on a maybe non-compact complete manifold, so where every geodesic can go as long as it wants, but with compactly supported functions and vector fields. The L2 inner product on C infinity function with compact support, so if M is compact, this is just C infinity. If not, this means things with compact support. The L2 inner product is the integral on M of F1 times F2 in the volume. So this is the scalar product that I was talking before on functions. And the norm is the square root of the scalar product between F and itself. Similarly, on vector fields, compactly supported if M is not compact, the L2 inner product between two vector fields is the following, is the integral over M of the pointwise scalar product between X and Y. Now we can rewrite some of the properties we wrote before. The definition of divergence is the following. Again, we are always in the case either M compact and no boundary, or M not compact but everything is compactly supported. So we can think about working on some really big open domain which encloses the parts where everything is non-zero. So on the boundary of this domain, everything is zero. So every time we have a boundary integral, it will be zero. Now, this is just a definition. The integral counterpart of the definition of the divergence. This is Green's formula. And actually, this here is the proof of Green's formula. Anyway, this is Green's formula in the case without boundary, because if you remember, the formula was integral, it's integral over u equals minus integral over boundary of u. But if there is no boundary, either because everything goes down to zero, or because the manifold is compact, so there's no boundary, that term is zero. And so this one was the integral over u of f1 Laplacian f2 minus f2 Laplacian f1 n in the volume. And then obviously you get the formula I wrote below, above. Now, again, this is the consequence of this first one. So, in the appropriate setting, I don't want to enter into details, but the operator of Laplace-Beltrami from C infinity functions with compact support to C infinity functions with compact support can be extended as a self-adjoint, positively defined, definite linear operator on a dense domain inside a Hilbert space. A Hilbert space is an inner product space, so an Euclidean space, possibly infinite dimensional. For example, the functions with the L2 product. Now, there are some details like dense domain and stuff like that, but somehow this tells you that the Laplacian is a symmetric operator with respect to the scalar product, and this tells you that it is positive definite. The linearity follows just by computations. You just apply Laplacian to f plus g and see what comes out. Now, why all this stuff? Well, because we have a symmetric a self-joint operator, so we can apply spectral theorem somehow. We can look for eigenvalues and eigenvectors and obtain an orthonormal basis of eigenvectors. Now, what does it mean to find an eigenvector for this operator? In our case, which is the zero boundary, we get the Dirichlet problem. So this is the eigenvalue or eigenvector, depending on which is your variable equation, Laplacian of u equal lambda u, and this is the boundary condition. This is what makes this a Dirichlet problem. Now, on a compact manifold, obviously the second part is empty because there is no boundary. Okay, but then it's compact. Now, spectral theory for the Laplacian tells you that either on a compact manifold or on a complete manifold with everything of compact support, this problem has a discrete set of solutions lambda. So we get numbers lambda, real numbers, greater or equal than 0, which form a discrete set, so they are spaced out. They do not accumulate, or you don't have an interval. I mean, it's not a finite dimensional thing. You don't have n eigenvalues. We have infinitely many eigenvalues. They could form an interval. They could accumulate on a point. They do not. In this hypothesis, they do not. So we get only what's called discrete spectrum. And each eigenvalue has a finite multiplicity. So this vector space of functions which satisfy Laplacian of u equal lambda u for fixed lambda is a finite dimensional vector space. For example, on a compact manifold for lambda equals 0, you get, obviously it's the smallest eigenvalue because they're all positive, and you get the constant functions, if m is connected, sorry. If m also is connected. If it's not connected, you get n copies of the constant functions. So, we take one, we discard the smallest eigenvalue. So lambda 0, we don't care about that. We take lambda 1, lambda 2, blah, 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 the positive eigenvalues. For each eigenspace, so solution to Laplacian of u equal lambda u, we get a vector space which is, whose elements are called eigenfunctions. We repeat according to multiplicity because every multiplicity is finite, so we get anyway a well-defined sequence. And now denote by u1, u2, etc. the corresponding eigenfunction such that they form an orthonormal system. You can do that due to the spectral theorem. We build a map for every m natural number, phi m from the manifold to Rm, given by evaluating at each point the first m eigenfunctions of these spaces. Obviously not the first one, because the first one will be the constant 1, so we don't care. A non-trivial result, not even that old, tells you that for m large enough, phi m is a smooth embedding. So, if you solve the eigenvalue problem, the eigenfunction problem, if you find eigenfunctions for the Laplacian, you get finite dimensional embeddings of your manifold, which have a number of properties being the eigenfunctions of the Laplacian. Now, why all this? Because, well, proving this is not, I mean, it's quite new, but it's not that difficult. And it obviously relates to something we already saw. Let me comment briefly. We saw this as a method for embedding a graph in Rn, somehow preserving distances along the graph or weights on the graph. And there are methods for nonlinear dimensionality reduction which are based on solving eigenvalue problems for some Laplacian metrics. Why? This is why. And this is the main ingredient for proving consistency and convergence of those methods. So why is that the multidimensional scaling, the And other methods we will see later that are based on the graph Laplacian embedding. Why do they work? Well, because if you make the points go to infinity, number of points go to infinity in a certain way, you are approximating the eigenfunctions of the Laplacian of the Riemannian manifold. Now, the whole trick is that, as opposed to the methods we saw already, the methods we will see in the next, probably already in the next lecture, I think. Yes, so on Thursday. The methods based on eigenmaps use the epsilon neighborhood algorithm for a graph, because we need the distances to go to 0, as opposed to the other methods which needed the graph to be connected, so uses the KNN algorithm. Anyway, this is the theoretical reason for which a number of algorithms we will study on Thursday work. And I think this is it for today.